Hi, everyone. In today's video, we are going to talk about creating a couple other types of graphs. We've already looked at very briefly the bar graph and a pie or circle chart or graph. Remembering that the word graph and the word chart can be used interchangeably. We use pie versus circle interchangeably. A bar graph or a column graph are similar, just which way you want to put the bars. We did talk briefly that every graph should contain a really good title, making sure that the title does refer to the data that you're actually looking at. Other things we want to make sure the graph is labeled, it has scales, things are complete. So these graphs that we're going to do in this video are ones that are a little less common. They're more statistically based and have their uses and also their downfalls. The first one that we're going to look at is something called a stem and leaf plot. These are still not very commonly used, mostly because if you have a large data set, they really are difficult to create. First of all, I have not been able to figure out a nice way for Excel or Google Sheets to do this for me. Yes, I can use Excel and Google Sheets to order the data, which will make things a little quicker, but ultimately I still have been doing them by hand. So first of all, there are two parts when you create a stem and leaf is you do keep every single piece of data. We're just basically ordering it in a nice systematic way. So we have a data point, and these are done using numerical data. And like, for example, we're going to have two pieces of that data. So you take your data point and you're going to break it up into two parts. One we're going to call the stem, and the other part we're going to call the leaf. Um, a lot of times the leaf, which is the second piece, is a single digit. So for example, they did tell us that the number 213 can have a stem of 1 and a leaf of 13, or a stem of 21 and a leaf of 3. I have seen more examples or illustrations of using a single leaf than I have the double digit leaf. So what we're going to do is I'm just going to kind of jump into an example and show you how it works. And the easiest way, I'm just going to, it's going to be kind of a, I don't know how I'd want to say this, but I have all these, our data from our earthquakes, and we can create what we're going to do is a stem and leaf. So again, we should have a title. Um, so I'm going to put on a good title. So you guys can create whatever title you'd like, but it should be something that has to deal with our earthquakes. And then what we're going to do is we're going to create our stems are going to come down be the first piece that we enter. And I notice that all of our data is 2 digits. We have a ones and then your tenths. And it looks like all of our ones are either an 8 or a 9. So those are going to be my stems. And then we put a bar, and we would list all of the stems. So if I did have like a 10, or maybe I had a 6 in here, I would put the 7 and the 6 because I do also want to show that empty space if there was any. The next thing I'm going to have to do is our leaves always get ordered from the stem out. And I'll show you an example of another one in just a bit once we get this one finished. So I'm going to just kind of go through my data real quickly here, and I see an 8.5, I think is my lowest value. So I'm going to write that 8.5. So I'm going to just write the stem. I'm going to see I have another one. So I'm going to write another 5. Don't see any more 5s, but I do see a number of 6s. So a 6, a 6, 6. I mean, I could do this in Excel, but I don't think Excel will do it for me, is the thing I was trying to get a point across. I mean, I could write the numbers 8 and 9 and then list these. It would not be a problem to do that in Excel or in a Word document. I have a 7 and a 7, another 7. There's one more 7. I think I've got all the 8 sevens. Oops, nope, there's one there. I have a 9, 8, 8, an 8, 8. But you'll notice I am ordering them from the stem out. I do repeat anything that is repeated. And I think I have all my 8s. Then I'm going to jump to my 9s. I have a couple 9 zeros. There's another one. Oops, one more. I have a few 9 2s. And then I have a 9 5, and it looks like I missed an 8 8. So I'm going to change that to an 8 and put another 9 in there. So kind of not a fun graph to create, but not a difficult graph either. Then what we do need to do is, because now our data is kind of gone, it's in this format. So we have to kind of tell our reader how to read this data. So I'm going to put a little key down here. So I'm just going to put my 8, and then I'm just going to pick a random leaf. And then I'm going to write that this is 8.7. And that would represent your 8.7, whatever those Richter scale measurements are. Yeah, so whatever that measurement unit is, I don't know what the Richter scale measures in. So that's kind of an example of a stem and leaf. Again, you'd have a better title than mine, and you have this piece up. You can sometimes break up your 8s and your 9s. So if I'd wanted to, I could have broke up my 9 and done like 9 0 to 9 4, and then this 9 5 would have been on the next line. Sometimes you can break up your 8s into a couple pieces too. So it really depends on your data. So this is a very simple stem and leaf. If you have 2 data sets, so here's an example already written. Doing 2 data sets, you should want to be able to compare them basically side by side. So if you're doing a stem and leaf, and you have 2 data sets, you're going to pick your stems that will work with both data sets. So they're talking about, in this case, how many partners the queen bee has. So we have 2 different species, and they count how many partners this queen bee has. And so we have our stems going down the middle. Okay, notice I did split these up. So then our leaves would be like 0 through 4, and then 5 through 9. So here would be my 0s to 4. So this would be my 4s. Here would be a 6. This would be the number 7. This would be a 12. Here we have a 14. This would be my 18, and so forth. But you can see them how they put them side by side. Notice also they did order from the stem out. So it started here with the smallest ones, went out, started here with the smallest ones, and went out. So they always start from the stem and work their way out. This was a slightly different way of writing the key. So you could have written it like they did here, that your stem represents the 10s and your leaf represents the 1s. Or you could have done like we did in the previous example and did something like this would represent 21 partners or something like that, partners. Okay, the way I interpret this, I see that they both look roughly symmetric, roughly normal-ish. It's hard to tell when there's not a big spread of data. I also can tell from this data set that species B, the queen bee, has a lot more partners than species A does. They tend to have fewer partners. As compared to species B. So a nice, easy way to compare. But again, we always order from the stem out. Nice title. They do have labels on both of these, and they do have our key for us so that we can read it. Another type of graph that is not usually done using Excel because again, they not a very common one. More commonly used would be a bar graph. So this is considered to be a dot plot. A dot plot is basically putting a dot for every single data point. So this is looking at what size shoe you wear. And so we have our size shoes down here. So almost think of it as a tally in a way. So someone comes on, tells you they wear a size 12, you put a dot for that person. The next person comes in, they wear a size 12, you put a dot on top of that. And you just keep adding dots as these people's shoe sizes are added. A little bit difficult to read because if we wanted to know how many people wore a size 10, we'd have to go and count the number of dots. So we do not have a scale on the y-axis to give us a count. We just have this picture of how many we have. If I were interpreting this, I almost see a bimodal, two kind of humps with a little bit of a dip in between, somewhat symmetric that I'm looking at. Most common shoe size is 8 to 10, which makes a whole lot of sense. If we were doing two data sets, if we wanted to compare two data sets, we don't put them side by side because that's kind of hard for us to see, like we did with the stem and leaf. And when we do a bar graph, remember we intertwined our bars one right next to each other for that specific category. In a dot plot, as we will see with some other graphs, we put them vertically on top of each other, but we use the same scale. So if you're trying to compare graphs, like a bar graph would even use this type too. We had one bar on top of the other bar. We want to make sure to use the same scale for both pieces so we can kind of compare them from one to the other. This graph is missing a title. This graph is showing us the age of students who take classes either during the daytime or during the evening. And we could interpret this if we wanted to, that the younger students tend to take the day classes, where the older students tend to take the evening classes. A little bit more spaced out as far as ages go. We didn't have any 21 or 23-year-olds, but again, we can easily compare the two graphs this way. But again, making sure to use the same scale for both graphs. It doesn't make sense to have two graphs to compare if they have two different scales. It would be harder for us to compare them. Okay. The next type of graph is one that is very used quite a bit, and it is used for when we are talking about continuous data. So numerical data and more on a continuous scale. So if we can have a frequency again, and we can talk about relative frequencies, we'll talk about that in a moment. But a histogram is a bar chart, so it's very similar to a bar chart. First of all, they both use bars. A bar chart usually uses categorical data or observations that are grouped into categories. Those categories could be numerical, like we saw in the earthquake data. We could have also created a histogram, I believe, with our earthquake data. We could have done that as well. But histograms, it is going to be numerical data, more so when we have continuous data. Again, the heights of our bars in both of them will tell you how many people were in that interval. The order in which we put these, we do want to put them in numerical order. A bar chart usually doesn't matter which way you put them in. However, if it is like the one we did with our earthquake data, I would want to have them in order because that would make a lot more sense. But if you're doing categorical data, truly just categorical data, a bar chart won't matter whether you put the number of people who like red before the number of people who like blue, will not matter. When we're talking about how many types of categories to have. Like we've mentioned earlier in other videos, there is not a hard and fast rule. However, we want to make sure that we have relatively few intervals if we have small data sets, and a little bit larger if we have larger data sets. So anywhere, they say anywhere from like 5 to 20, again, depending on how much data you have and the span of your data. The rule of thumb for that I've seen in this textbook anyway says that the number of intervals should be roughly the square root of however many observations you have. So if you had 100 observations, you'd have roughly 10 groupings would be a good way to start. You can adjust a little bit. Like they've said, there is no hard and fast rule. So sometimes you have to play with your data a little bit to figure out what classes work. Your relative frequency is just, instead of having how many or the frequency along the column, they will have you calculate the relative frequency, which is kind of like a percentage in its decimal form for the number of people in that group. And we calculate that by taking our frequency and dividing it by the number of observations. And we will get a decimal, and you could turn that decimal into a percentage as well, but we keep them in their decimal form. Things that we kind of look for in the histogram, just like we did for other data, other graphs, is we look for where is the middle, the center, whether it be an average, a high point. We kind of look for our spread, how spread out is our data, the general shape, so the number of peaks, same things that we did before. We look for any outliers and any gaps that we might have. So those are just some things we kind of look at, which is what we've looked at in other data as well. So I do have an example. Well, did actually just draw the graph for this, but so here is a farmer who's interested in how much his tomatoes weigh. And so he collected 20 tomatoes and recorded how much they weighed in ounces. To save a little bit of time, this data is ordered. And so we have some classes that were created for us. We went from 2.5 to 3, and then 3 to 3.5. The thing to remember when we are doing a histogram is these intervals will slide from one right into the other. And by rule of thumb, when they just write 5.0 to 5.5, something like this, they are going to include the 5.0, but not include the 5.5. The 5.5 would go in this other value here. So like when we see this 3.0, that 3.0 is counted here in that 7 count, as opposed to in the count before it. So we include the bottom, but do not include the top. And that's just kind of a rule of thumb that we came up with, or someone came up with when they created these histograms. And so very similar to a bar chart. So we do get our frequencies just by counting how many are in each group. And when we go to create our graph, instead of writing like we did before, instead of writing our interval underneath, we actually just put those boundary values to represent the scale. And then our bars will actually then touch one another. So here our bars are going to touch. And we have more of a scale used instead of categories. Sorry, I would say labels. Okay. They still do put the labeling up for the actual axes down there so we know what those numbers mean. So you'll notice, again, we just have the scale down here like you would on a number line, as opposed to writing that, like the 25 to 3, 3 to 2, 3.5, and so on. And again, remembering The bottom number is included. The next number would be in the next grouping. So again, how I went through with that 3.0. Okay, this is considered a frequency histogram. Frequency histogram. Because we have frequencies along the side. So 0, 1, 2, however many were in there. If we wanted to change it to a relative frequency histogram, the only thing that is going to change would be our scale here. So this, instead of just being frequencies, it would be relative frequencies. And I would probably keep the same sort of scale. So I'd have like, and we had 20 total. So if I took take my number 1 and divide it by 20, I get the number 0.05. So this will be like 0.05. This would be 0.1, 0.15, 0.2, 0.25, and all the way up. And then when I have my 3, if I took 3, because I'd have another column here maybe, and I'm just going to do a couple of bars, relative frequency. I would take my 3 divided by 20. That gives me 0.15. That will tell me that that first bar. So here's my 2.5. Here's my 3.0. Again, we'll still label the bottom as it was above here. And we'll have that bar at 0.15. The graph will look exactly the same as this graph. The only difference will be how we have the side labeled. The y-axis is just labeled with the relative frequencies instead of the frequencies. Okay, so that is your histogram. Again, you'd want to have a good title on both of these to make sure that the graph telling you that this is be the weight of these tomatoes that this guy chose. Okay. If we had 2 frequencies, very similar to comparing, we want to use relative frequencies to compare, because then we aren't going to be comparing different sizes of data sets, because everything would be on a 100-point scale instead of having different groupings. So you might say, oh, this one has 15. Well, this one only had 30 to begin with. So we are able to compare things a little bit easier. So if you're using histograms and you are going to compare 2 data sets, you want to use the relative frequency to make your decisions, because then they're a little bit more on the same page. And again, like we did with the dot plots, we use a similar scale. So here's our scales, and notice they are relative frequencies. Here we started with the current cable and the new cable. Notice here the new cable is a lot faster than the old cable. You can see that this one is kind of bell-shaped. This one's a little bit less bell-shaped, a little bit flatter. I wouldn't say it was bell-shaped. I would say it's probably not really symmetric either. So maybe a little bit skewed one way or another. Okay. The last graph that we're going to look at in this section, we will talk about another one later. We will look at a box plot, which was mentioned in the notes, but I skipped right over that. We'll come back to that a little bit later. The last one we're going to do is how we construct a cumulative frequency or a cumulative relative frequency graph. And again, this is used for continuous data only. And so we could do a relative cumulative frequency or just cumulative frequencies. These are called an ogive. So if you want to think of how you pronounce it, it's like with a J-I-V-E. So like with a long I. So it's an ogive. What we do is we are going to end with that 100%. So I'm going to be doing a cumulative relative frequency. You could do one with just frequencies, but they are used more often with the relative frequencies. So again, we're going to start with one variable. Our data, we do want to use numerical and when we're trying to do cumulative amounts. So first of all, cumulative means we're going to be adding up as we go. So kind of think about it as snow falling. So, or as we're, in this case, I'm going to be talking about, I've got this bucket of tomatoes and I'm going to be just keep adding to my bucket and eventually I'm going to get all 100% of my tomatoes. So I'm going to use the same data that we did before. So there's our tomato data, and here's our frequencies. I'm also going to put in my column here and use and create the relative frequencies. So as we mentioned before, to calculate those relative frequencies, we take that frequency and divide it by our total. And using my calculator, so 3 divided by 20 is 0.15. 7 divided by 20 is 0.35. 0 divided by 20 is still 0. 4 divided by 20 is 0.20. 3, and then 3. Okay, I'm going to create another one, cumulative, which means I'm going to start my bucket. And by the time I get through this category, I have added all 3 of those tomatoes to my pail, or I've got 15% of my tomatoes in there. As I continue through, I'm going to be adding on the next group. I'm going to be adding them into my bucket. And so I'm going to add on that 35%, which brings me up to 50% or 0.5. I'm adding on another 0. So adding 0. I'm going to be adding in my 20%, so 0.7. Adding my 0.15, so I get it up to 0.85, or 85% of my tomatoes are going to be in my bucket. And then when we add the final, we should get up to that 100% or 1. And these are the numbers that we use to create our ogive. Okay, so again, to create a graph, we will have a good title. I'll let you guys choose your own favorite good title. Here we will have our axes, just like we did before. So here I'm going to have what we have, the cumulative, relative frequencies. I'm abbreviating just to save a little time. And I'm going to count by 0.05s. 1.15, 0.25, oops, 0.2, 0.3, I'll skip a few, 0.4, skip a few, 0.5, 0.6, 0.7, 0.8, 0.9, and 1. Okay, so I have my scale. Maybe I'll move these numbers over here. We started at 2.5, then 3, 3.5, 4, 4.5, 5. I'm using the exact same scale that we did when we created our histogram. So this is the weight in ounces. Okay. And what we do is before we had any tomatoes, our tomatoes bucket was empty. So we started at 0. Then I hit this 2.5 ounces, and that's when I started adding tomatoes to my bucket. By the time I hit 3, my bucket had 3 tomatoes in it, or 15%. So when I'm hitting here, I got to 3, and we're going to connect our dots. And then by the time I got to the end of 3.5, I had 10 or half of the tomatoes in my bucket. So I'm up to 0.5. And we connect our dot. Then we added nothing, so I'm going to stay there. I'm going up to 0.7, trying to do this. Would have been much easier to do if I had gridded paper, but that's okay. And then we're going to go up to 0.85, and then up to 1. So you can kind of look at that would be your kind of your cumulative piece. And here you can kind of see that we did have to, we grew a lot more in there by the steepness. A little harder to tell how many are in there, but this does have its reasonings for it. So if I wanted to know percentiles, we can use this graph. We will talk about that when we actually talk about percentiles. But this is your cumulative relative frequency graph, or a cumulative ogive, or a relative frequency ogive. So depending on how we draw those. I do have a few more, and I'm not actually going to draw the last one because it is relatively easy to do in spreadsheets and things like that. So the first one here, we are going to skip right over the box plot. We will come back to that when it's more appropriate. The last graph that I'm going to talk about is your time series graph. A time series graph or a time plot is something that is collected over time, data that's collected over time. And what we look for is interesting trends or patterns. Is it going up? Is it going down? Is it jumping all over the place? Again, when we're going to use this is when we're talking about something over time. The data is numerical. We do use a line graph for this. So what we do is we plot a series of dots and we connect our dots. So we would enter the graph into our spreadsheet. Your 0 is one under the months, 19 is that height. So this would be my X's, would be my months. And then my heights would be the Y values. If I were using Excel, I do not use the line graph. I use a scatter plot to graph these because then I can actually get the dots that I want and it will connect them for me. So if you're in Excel or if you are using Google Sheets, look for that scatter plot versus your line graph. You could try a line graph, but it's not going to work as nicely for you. And maybe if I think I still have my thing open. Maybe I will go to Excel or my spreadsheet here. So I do not have it open anymore. But yeah, I would go through that and just make sure, try it once and just see what happens. Because remember, we're going to be looking for a single line as opposed to double lines or triple lines. So this one, we should have only one line showing up that goes through these points. So make sure when you're doing your graphs, you actually get what you look for. A lot of times I'll have students that will graph it and turn it in, and then I look at it and I'm like, did they even look at this graph? Because a lot of times it'll have two graphs. Like it'll have the point 1 versus 0, 2 versus 2, 3 versus 4, and then it'll also have 1 versus 19, 2 versus 21, 3 versus 24. So it's not graphing what they want it to graph. So make sure when you do make graphs or charts that you look at them and say, is this what I wanted it to look like? Also make sure that your graphs have good titles, labels, scales, everything that it needs. And also make sure if you're asked to create a bar graph, that you create a bar graph. If you're asked to create a pie chart, you do create a pie chart. And in pie charts, remember, we include percentages. So this has been a quick, very brief overview of graphing and how to kind of interpret them and look at things and try to get some data from them. So hopefully we'll be jumping to something a little bit more statistical in nature next. So I look forward to seeing you guys in more and future videos. Have a great day.